Okay, so we have a relationship between the original data and the original model and the original coefficients and variables and the standardized one. Um, so think about it. We start with our original data, we transform it into this centered and normalized vectors of data, and then we would proceed to estimate to find a linear fit for that data. So that's where we are now. So to estimate, to find B star, the little b star, the estimated regression coefficients for the standardized model above by the correlation transformation. Above, we solve in the least square sense, right? We solve least squares solve. Y star equals, let's write it in matrix term, X star B star. So this would be n by 1. This would be p minus 1 by n. And this would be, let's see, wait a second, what the hell? N by p minus 1. Yeah. Right, so this is n by p minus 1, and this is p minus 1 by 1. Okay, right. All right, so, right, just like before. So we solve this, we find the least square solution b, little b, that solves this. Okay, so proceeding exactly as before. Oh, and X star now is a matrix, but it has, as you see here, it doesn't have p columns, it has p minus 1 columns because it's missing the column of ones, right? So it has x11 star dot 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 x n1 star x 1 p minus 1 star and x n p minus 1 star. Okay, all right. So, and then B star is the B1 star. These are the estimated regression coefficients. And Y star was defined above. All right, so again, same thing as before. We set up the least squares equation based on the shortest distance and minimizing the distance from xb to y, and we get through that same magic, b star equals, or geometry as I prefer to call it, x star t x star inverse x star t and y star. And of course here this inverse exists because the columns of x are independent. If they weren't independent, if you could write one as a linear combination of the others, you could reduce your model and lose absolutely nothing. So you would certainly do that in that case. You'd be glad if they weren't, if they were dependent in some ways, and then you could exploit that. Okay, so here we are here with b star equals this, and before we go into getting any closer to a solution, of course you could just do this again and compute it this way, but there's another way to look at this. So this is very maybe a lot of the reason why we're here looking at this. So we're going to go look at this now. So b star is equal to this, and we would like to break this into two pieces here. So I want to look at this piece as one piece, and this piece is another piece, and look at B star as the product of these two things. Before we do that, we have to have a few more definitions about correlation. So if we can hang in there a little. This lecture on standardization is just 10 hours long, okay? So it'll be over soon. So we define, say, let U, and I want to use different names, U and V be vectors of same length, or same size, same number of elements. Then we can write core UV, the correlation of U and V, which we might write like this, little r UV, is defined to be the sum. So n is the size of same size n. Ui minus U bar, Vi minus V bar, all over square root and this should look a lot like the expression for correlation, right? So for random variables. Okay, but this is like a sample correlation. So we could call this, and we can call this, and this called let's see, sample correlation, or coefficient of simple correlation, or just correlation. Okay, so it's obviously these are constant vectors, so the vectors of observations, so this is the only thing that would make sense. This should look a lot like the expression for correlation. We know if, so should look like, so this should, you should be able to figure this out without having to look it up. So this should resemble the correlation for two random variables, say, let's call them something else like W and Z, where W and Z are V's. So we get this is equal to right? So that looks like the top. And then on the bottom we have, so on the bottom we have the square root of the variance. So this is the covariance here. And on the bottom we have the square root of the variance. So we would have square root square root okay, so these are just, we're taking averages here instead of expectations, best we can do. Okay, now really the variance here has a divided by n minus 1, divided by n minus 1. This has a divided by n minus 1, but they all cancel. Okay, you get a square root of n minus 1, square root of n minus 1, and that cancels with the unsquare rooted n minus 1 up here in the top. Sorry, maybe I should have call it quits for the night and do the rest tomorrow. I'm getting sloppy. Okay, so if you accept this new definition of correlation of two vectors, actually, maybe we should do an example. So for an example, suppose we have, let's say, u equals 0, 1, 2, 4, 0, and v equals 1, 3, 5. Let's say it goes down now, though, 3 and 2. Then correlation UV equals, I can let you do it, work on it for a minute. Well, using this formula up here for the sample correlation. So I want to take pairwise products and add them up. So we get on the top, I get, oh, first I have to center them, right? And then it's all the pairwise products and stuff like that. So what's the mean here is 7. This is brutal. So you can use R, correlation UV. This is 7 here. Maybe we should make it, change it. Let's make this 7. Okay, so the mean is, so the mean is 2 there. And is this mean, this is, let's see, let's make this 2. So the mean is 3 here. So if we make these changes here, what do we get? We get u minus u bar is equal to, let's see, 2, right? So minus 2, minus 1, 0, 5, minus 2. V minus V bar is equal to, mean here is 3, minus 1, 0, 2, 0, minus 1. And correlation of UV is equal to, I take the pairwise products in the numerator, so I get 2, 0, 0, 0, plus 0, plus 0, plus 0, plus 2 on the top. And in the bottom, I get, okay, here I'm squaring each and taking the square root. So I get 4 plus 1 plus 0, so that's 5, 30, 34. And the other one I have 1, 4, 1, 6. 6. So 4 will come out. Will an 8 come out? No, 2. Yeah, just a 4 comes out. So I get a 2 coming out. So I get 2 over square root of 51, right? Okay, so slightly positively correlated. It's not a very big number. Well, square root of 51 is like a little bigger than 7, so it's going to be like 0.2 or something, 0.15 or something. Okay. All right. Okay. So for practice, suppose little w is equal to 6, 1, 10, minus 1, 4, and find core UW and core VW. Oh my God, we gotta stop.